This is problem 1317 on page 822. The subway train shown is traveling at a speed of 30 miles an hour when the brakes are fully applied on the wheels of cars B and C, causing them to slide on the track, but are not applied on the wheels of car A. Knowing that the coefficient of kinetic friction is 0.35 between the wheels and the track, determine A, the distance required to bring the train to a stop, and B, the force in each coupling. Now we can cheat just a little bit here and know that we are dealing with a work energy type of problem because that's the section it's in. However, another thing to note is that they asked about distance. These are forces and distances. Anytime you hear force times distance, you should think work energy. If you hear force time, you should think momentum. Okay? So let's analyze this. We've got three cars connected together. I don't know why the lead car is so large. I guess because we're having to slow it down. Really, it's not. It's 40 tons. The middle car is 50 tons. And the last car, these are A, B, and C, is 40 tons. The nice thing about the work energy method is while you might make a free body diagram, you won't necessarily use all of the forces because they don't really matter. And we know that the system has a velocity of, 30 miles an hour? Yeah, 30 miles an hour. And we want to know how far before it comes to rest, right? Okay. So the coefficient, last thing, the coefficient of friction was what, 35%? Yeah. I don't know how I want to write that. Mu equals 0.35. It's applied there and there, but not there. Okay. So of course there's going to be some friction forces. And those friction forces are at their maximum. How do I know? Because it's sliding, right? So I know that the friction force on car B will be the friction coefficient times the normal force from car B. But of course, I realize that the car is not accelerating up and down, and so the normal force equals the weight force in this case. So this is just the weight of car B. Similarly, the friction force on car C is mu times the weight of car C for this case. Okay. So the total force tending to slow down the train is FB plus FC. Another way to say this, these are the two forces doing work on the train. Because if we look at the equation, we usually write it like this. But this is nothing more than an energy balance, and we can consider the whole train as one entity, right? I know we have to break it up to consider what the magnitude of the forces, but we can consider the whole train as one entity, or you can think of it as three separate entities where we're adding up all of the kinetic energy of all the cars, right? And all the work done on all the individual cars, which are part of the system, to calculate the final kinetic energy. But what is the final kinetic energy? It's zero because it comes to rest, right? So this first term, I need something like 1/2 mv squared, but if I've got three masses, I may as well use a total mass here because that's the kinetic energy of the whole system, all three cars together. And there is work done by the two friction forces. Is that work positive or negative? Well, the motion's that way, the friction force is that way, so it must be negative, right? So what I need here is a negative sign. F sub B multiplied by what? Well, whatever distance that force gets to act through to bring all the cars to rest. But by the way, there's another force helping out. That's the friction force from the brakes in car C, also acting through that same distance x to slow it down. So basically what we're saying here is the distance x, I won't go that fast, times FB plus FC is equal to 1/2 total mass V squared. Where V, by that I mean the initial velocity. Okay, just rearranging it a bit. And so x equals 1/2 total mass V squared divided by friction force B plus friction force C. But we already know that the friction forces are mu times the weight of B plus mu times the weight of C. And oh, by the way, we could factor out mu, couldn't we? Mu. But the weight of B and the weight of C is nothing more than G times, so we'll factor it out too, the mass of B plus the mass of C. But the mass up here, the total mass, is the mass of A plus the mass of B plus the mass of C. See? So, basically the distance that we need in order to stop is the total mass, which is what? 40 and 40 is 80. 80 plus 50 is 130. I don't remember if tons are technically weight or mass, times 30 miles per hour squared divided by, I'm going to take this 2 to the denominator. The friction coefficient, 0.35. G, well, we're in English units, 32.2 feet per second squared. Mass of B plus mass of C, well, that's 50 plus 40 is 90 tons, and now it doesn't really matter if that's mass or weight, it'll cancel. Okay. And, by the way, we've got a little bit of a units mismatch because we're measuring miles and feet and hours and seconds. So, what do we need to multiply by to take care of that mismatch?
52.
So, 5280 feet per mile. What else?
Divided by 3600.
So 1 hour per 3,600 seconds. And then what do we need to do?
Squared.
We need to square it. Because we got miles squared over hours squared. We've got to get rid of all of that. So all of the miles and hours will go away. What will we be left with? Feet. Because we got feet squared per second squared over feet per second squared. Second squared go away, we're left with feet squared over feet, which are just feet. So please calculate for me, if you would, how much distance is required in order to get this train to stop. I'll calculate it, I guess, at the same time.
That is not.
Should we have measured the distance in miles?
124.07 feet.
I'm already committed to calculate it myself, thank you. I'll calculate it as well. 124 feet, is that what you got? Yes. That's what I got. So 124.07 if you want feet. Yeah, that's arrogant. There. Stops in about 124 feet. How about the force? Why would we care about the force between the coupling? Well, because these two cars are hanging on to that one, right? Keeping it for trying to brake it and slow it down. I don't know if the brakes on car A failed or what. But we'd like to figure out the force in this coupling. How can we do that? The only way to do that is to consider either car A by itself or the other two cars by themselves. Take your pick, it doesn't matter. I'm going to choose car A. And I'm going to apply the work energy equation to that as well. Why did I choose it? Well, because I think there are going to be fewer forces. There's just one force in that case. You can say, yeah, but you don't know what that force is. That's okay. That's what I'm trying to find. I don't like, yeah, let's call this P, just the pulling force. Slow it down. Because see, now we know how far this pulling force acts through in order to bring that 40-ton car to a stop. So we can write the same thing again. T1 plus U1 to 2 equals T2. T2 is 0. And now I'm talking about the kinetic energy of just car A, right? So 1/2 the mass of car A times the initial velocity of car A squared Why don't we convert this to feet per second? What is that, 30 miles an hour? What is that in feet per second? 3 times 5280 over 3600. 44, there we go. That way we can stop dealing with miles per hour. 44 feet per second minus P times X equals 0. Because look, this pulling force P acts through this distance X of 124 feet. We know that at that point, after that force has acted through that distance, there is no more kinetic energy in the car. So now we can solve for the pulling force P, and that would just be 1/2, in fact here, let's just do it this way, 1 over 2x, or MAV squared, over 2x would be equal to P. Okay? So, the mass of car A is 40 tons. We need a velocity squared of 44 feet per second quantity squared over 2 times, let's see, X is 124 feet. And notice
Need a conversion.
that we'll have to convert tons into mass, into pounds meters. So how many pounds are there in a ton?
2,000.
2,000. So there's going to be 2,000 pounds mass, right? Again, I don't know if tons or mass or weight, I don't really care. Because 2,000 pounds force or 2,000 pounds mass will weigh 2,000 pound force on Earth, so it's fine. Okay. So let's see. However, this will leave us with units we don't like. Well, let's go ahead and calculate it. So tell me what the number is, if you would.
624,516.
And what are the units? Pounds mass feet per second squared, right? Because we got feet squared per second squared divided by feet, so that's just feet per second squared times pounds mass. But those are not force units we are used to using. Is this a valid unit of force? Yes. A pound mass foot per second squared is a valid unit of force. You can't go down to Target, though, or maybe Walmart, and buy a scale that measures in pounds mass feet per second squared. Okay? But you can convert your weight, if you have something that measures pounds force, by just multiplying by 32.2, because there are 32.2 pounds mass feet per second squared for every pound force. In our case, we're dividing because we already had pounds mass feet per second squared. If you want to know your weight in pounds mass feet per second squared, no problem. Take your weight in pounds force, multiply by 32.2. There you go. So divide your number by 32.2 if it's still in your calculator.
19,395.
2,395. That's how hard car A has to be pulled. We could, but then we'd be confusing whether tons are mass or force. 2,000 pounds force is a ton. I don't really know which one's which. I don't know if we even have a conversion factor to tell us. Let's find out. What was it, page 12? We found the conversion factor table. Let's see what they call it. Ton. They have it under mass. So we'd rather not convert it to tons.
So whenever someone says it weighs a ton, they're wrong.
That's right. It has the mass of a ton. At least according to this book. But I guess that's the answer to part B, isn't it? So we should probably put a box around it. Any questions about this problem? I have a question for you. If this same train were on the moon, same mass, would it stop in the same distance or a different distance?
No, it would take longer. Well, no, because there's less mass.
It's the same mass.
Less weight.
What does your intuition say?
That decreases the normal force, so.
My intuition says it would take longer.
Yes.
See G right there? So the smaller G is, the bigger X is going to be. And on the moon, G is smaller, so X would be bigger. So your intuition's correct. It would take longer to stop this train on the moon. The train still has the same amount of mass, but we can't apply as much friction force to it because we don't have as much weight to generate that friction force.
But also means that the same amount of momentum, right?
Yes. we
Which
have the
is
same amount
why
of
it
momentum.
would take longer to stop it.
Well, it'll take longer, you said time, so we're gonna talk about that. It'll take a longer distance from this, but once we study impulse momentum, then yes, we'd also find it takes a longer time to stop it. Any questions on this problem?